Hello everybody, and today we'll be talking about The Elements, which is a book written by Euclid. It was the modern foundations of geometry, actually. A fun fact, in England, the kids at school learn much more geometry than, for example, we do here in the Netherlands. And I think some schools even use The Elements as a textbook, geometry textbook. So some of the viewers from England might already know The Elements and how it works and everything. But we'll be going over it today. So what is it? What is in this book? Well, first of all, Euclid makes some definitions. Because if you want to talk about something, you have to make clear that everybody knows what you're talking about. And there are 23 definitions in this first book about geometry. We begin with the definition of a point. A point is that which has no part. Is stated, so a point has no part. Well, what does that mean? Well, if you know what a point is, it makes sense, but perhaps to someone who has never seen a point, it would sound a little bit abstract. But that doesn't matter. The second definition is a line. A line is a breadthless length. So breadthless length. And so a line has no width. It's infinitely thin. And a point is zero-dimensional. It has no part. And then we go with the end of lines are points. So if you have a line and it has an end, then these are points. And then it defines a straight line. A straight line is a line which lies evenly with the points on itself. And so if you imagine a straight line, all the points lie evenly with itself. And etc. He defines all kind of things like surfaces, edges, angles, obtuse, acute, boundary, a circle, semicircle, equilateral triangle, what parallel lines means, all kind of things like that. And then we come to the second part, which are the postulates. So then we have postulates, and there are 5 of them. And these are the famous 5 axioms that he made. So these things he just assumes to draw conclusions from later. And when you look at the Greek translation of postulate, it's not really an axiom. It's not really like he assumes these to be true, but more that he demands them to be true in such a way that there could be places where these aren't true, but he's not looking at those places at this moment. Instead of just assuming these are true because he thinks they are true on a Euclidean plane, which is just a 2D piece of paper. And the first one is that it is possible to draw a straight line from any point to any point. So if you have 2 points, you can draw a straight line between them. And so we can't have a surface with a hole in the middle or something like that. And if you had an annulus and you want to try, well, can I maybe, so this is not 3-dimensional, This is just two-dimensional annulus. So, well, maybe I could apply Euclidean geometry to here. Well, no, that wouldn't be possible because you can't draw a straight line from this point to this point. And because this space isn't there. So that we immediately cross that out. It's possible to draw a straight line from any point to any point. Then we have the second postulate, which is that you can draw a finite straight line continuously in a straight line. So if you've got a straight line, you can draw a finite continuous straight line inside it. So that's also quite obvious. So that's just you can really imagine a space where this wouldn't hold true. Then we get to the third postulate, which says that you can describe a circle with any center and any radius. So if you get a given center, we've got a given distance as a radius, and we can always draw a circle with that radius around that point. Okay, that's also quite obvious. Then the fourth one, all right angles are equal to each other. Well, that's also quite obvious. And if you got a right angle up here, got another one up here, well, of course, they will be equal to each other. You might ask, well, why would you need to postulate this? Well, this seems to be to prevent things from a cone to be able to be part of Euclidean geometry, because you have to look back for how he defines a right angle, and it turns out that he defines it as when you have a line, a right angle cuts the space on one side of this line in half. So you want this space to be the same as this space, so cut it in half, and it turns out if you are at exactly this point of a cone, the total angle around this point is not 360 degrees. So you wouldn't be able to, you can cut it in half, but then that wouldn't be a right angle. So that's why we would include something like this. Okay, so all of these are very easy, very logical that they would be true on a flat piece of paper. So obviously that would also be true for the fifth postulate, right? Well, not really. Let me state the fifth postulate. If a straight line falling on two straight lines make the interior angles on the same side less than two right angles, then the two straight lines, if produced indefinitely, meet on that side on which are the angles less than the two right angles. That's the total statement. Well, that sounds like a huge statement, and what it's actually saying is that we have two straight lines. Then we have two straight lines, and we have another line meeting them. And it makes the interior angle on the same side less than two right angles. So for example, here the two angles are less than two right angles added, so less than a total of 180 degrees. Then these two straight lines meet on this side, so you can extend those two. You would see that eventually they'll meet. Well, that's kind of a strange postulate, and many people have thought that, since Euclid has tried to replace it with other postulates, showed some things are equivalent. It has to do with this statement turns out to be equivalent to the fact that if you have a parallel line and a point outside of it, that you can draw exactly one line parallel to this line through this point. And it turns out it's not necessary. You can drop this proposition, this postulate, and you can assume that there are none lines going through this point, or infinitely many, and those will give you elliptic geometry and hyperbolic geometry respectively. So that's something to look into, but it's not what we're doing right now. We're doing Euclidean geometry. Then we have some common notions, some things which he also kind of assumes. It's like things which equal the same thing are also equal the other. Kind of a transitive assumptions. So if you have x equals y, it's together with y equals z, then it turns out it follows from this that x equals c. That's actually what he's saying, with x, y, and z being some geometrical object. Then he says if equals are added to equals, then the whole are equals, and so equality, not with his symbols but inside of his notion, is additive. So two things are equal to two other things, you can add those first two and those will equal the sum of the other twos. And so a equals b and c equals d implies a plus c equals b plus d. That's what he's saying. And also with the difference, that's the third common notion. Then the fourth common notion is things which coincide with one another, equal one another. And so if you had a line segment, you had another line segment, and you could slice this line segment to there to make it coincide, and then you know these line segments are the same. And the fifth common notion is that the whole is greater than the part. So if you have something and you have a part, then you know this is less than the whole. That's also the fifth common notion. All very obvious to assume them. And then he gets to prove some things. So we get to the propositions. And in total there are 48 of them in this book. And he starts by saying, given a finite straight line, we can construct an equilateral triangle with this straight line as a side. And well, you know, we've assumed that if we have a point and we have a given distance, we can make a circle with this radius. So make a circle around this point. That's a very bad circle, but assume it's a circle. And do the other thing with this point and this length around this. And then choose one of these points. And this will form an equilateral triangle. And because if we look at this circle, all radiuses are the same. And that's how a circle is defined, as all points with a given radius form a point, given distance. And so this distance is equal to that distance. And we know from this circle that this distance is equal to that distance. And so by the common notion that things are equal to the same, namely this length, are equal to each other, we see that all the three sides are equal to each other, which is the definition of an equilateral triangle. And so you see all of these things he assumed and defined before, they are coming back in the proofs, which is kind of obvious, but it's nice to see. Then he says something about if you have if you have a line segment given and you have a point, then you can transfer this line segment to this point. You can make another line being at this point and having the same length, which is already much harder to prove than this first thing about equilateral triangles. We're not going to do it right now, but that's his second proposition. What's nice to see is if you look at the proof is that in that he uses the fact that you can always make an equilateral triangle with a given length, so that's quite nice. Then he has his third proposition. I say that if you have two line segments, you can, where one is bigger than the other, you can cut off, you can find a point in this line segment that has the same length as this, so you can cut off a line segment from this bigger one that equals the lower one. And he does that first by saying, well, I've got a line segment and a point here, I can make that point be at this line segment via what he net proved up here, which we didn't prove, but you can make this line segment go to here, and then you can draw a circle around and make this intersection point, and then those two things are the same, because that's how circles defined. And circles are always possible to draw because that's also something we assumed, and of course because this thing is equal to this thing and this thing is equal to this thing, we know this thing is equal to this thing, and because of our notion of equality, and one of the common notions. So that's also a very nice proof. It's already, which is again a bit simpler than this second one, kind of an outlier. And then as fourth, he says something about congruence. So he says that if you have two triangles, which he already defined before, and you know that these two sides are the same, and these two sides are the same together with this angle being the same, then we know that the rest of the angles are the same. So this angle equals that angle, that angle equals that angle, and this side equals this side. And he does that by placing this line segment on this line segment, which is possible, etc., etc. Then this angle will fall together with this angle. That was one of the common notions, things which coincide with one another, equal one another, but then the other way around. And then, of course, this line segment will fall on this line segment, so those 2 points will fall on that point, and we see that this line segment will be the same and those angles will be the same. And you make such an observation. Kind of nice. It's the first proof that's not constructive like these ones. So you have an explicit construction. This is another way of proof. It's not that you want to construct something, that you want to say I'm able to construct a certain thing. He's able to make a certain conclusion about lengths and angles. So that's nice. And then you got a whole lot of other propositions which each follow from each other. And then in the end, proposition 47 and 48 together prove Pythagoras' theorem, with the Pythagorean theorem. The first one by saying if you have a right angle, then a squared plus b squared equals c squared. And the other one says that that's this one, and the other one says that if a squared plus b squared equals c squared, then you know that you have a right angle, which is kind of nice. To end, I want to give you a little idea of how all of these things depend on each other. And so in the first proof, in the second proof we use the first, etc. So here's a table of it. And we can see in the beginning that indeed the second proof uses the first one, the third proof uses the second, etc. So we've got all of these dependence relations. And at the bottom we see that that in the proof of the other way of Pythagoras' theorem we used the first way. So you could see all kind of nice things in this, but to give you an idea how this would look like. But that's it for now.